So you start by getting down these notes. And these notes really are kind of everything that you learned in geometry about trigonometry. These were all the big things. It was like you had the definition of sine, cosine, and tangent, but those definitions, they all went back to this picture over here. Now you should be able to look at any picture of a triangle now and tell me which side is opposite, adjacent, and hypotenuse. Now how do you know? In this particular picture, notice the little arc in this angle right here. That is showing that this is the angle that everything is going to be relative to. We always need to know which angle we're going from when we do one of these, because the opposite and the adjacent, they change based on that. So it's all going from that particular angle here. Now when I'm doing one of these and deciding what is the opposite, adjacent, and hypotenuse, the very first one I always look for is the hypotenuse. Because the hypotenuse usually jumps out. There's two ways that you can know which one's the hypotenuse. One is, it's always the longest side in a right triangle. So that can give it away right there. But if not, it's also opposite the right angle. Every single time, the hypotenuse is on the opposite side of the triangle from the right angle. And so that's how I know where the hypotenuse is. Once I know where the hypotenuse is, then I think about what is the opposite. And if you train your brain to always look for them in this order, life gets a whole lot easier with these. So the next one I look for is opposite, and that is literally on the opposite side of the angle that we're told that we're going from. That's why we have to know which angle we're going from, because if I was going from this angle up here, it would change which one was opposite. So we always have to know which one we're going from. And then the adjacent, that's the remaining one, because if you know which one's hypotenuse and which one's opposite, process of elimination tells you the adjacent. The adjacent in general means next to. So it's the side that's next to the angle, but of course there's two sides that the angle is touching. It's specifically the side that the angle is touching that is not the hypotenuse. And so those are some ways to know it. Now once you know how to name them, then these things over here, these fractions, start to take on a little bit more meaning. Now the whole idea behind sine, cosine, and tangent is that each of these represents a given ratio of the side lengths for any given angle. So for instance, if I tell you what the angle is, then I will know that sine of that given angle equals some number. No matter what the side lengths are, the opposite divided by the hypotenuse length, if the angle is 60 degrees, it will always give us the same thing when we divide them. It comes back to the idea of similar triangles and how if you multiply one side by a constant, you got to multiply every side by the constant and stuff like that. So really, sine, cosine, and tangent each represent the value of a ratio. Now, the other thing I want to make sure you kind of got your head around here when it comes to sine, cosine, and tangent is that each of them are functions. So just like square root is a function, or just like logarithm is a function, so are sine, cosine, and tangent. Basically, if we plug some number into it, it does a very specific operation to it, and it pops out something of meaning to us. In this case, like sine pops out what that ratio of opposite divided by hypotenuse would always give us. Things like that. All right, so now that we have that, you are going to need to know those by heart. And if you forgot them from geometry, well, it's time to remember them again. Now, do you remember the easy way, at least hopefully easy way to remember each of these three definitions? Yep, SOHCAHTOA. If you don't remember that, you might want to put it into your notes here because it's a nice reminder that by remembering this one word, you can actually remember all of those definitions. The way it works is that the S here stands for sine. Well, what's the definition of sine? Opposite over hypotenuse. SOH tells me that sine is opposite over hypotenuse. It tells me which sides are going with that. The C, well, of course, C would be cosine then. And cosine, you can see it goes CAH. So cosine must be adjacent over hypotenuse. A nice way to remember that. And then tangent, well, that's our T, of course. It's OA. So that means it must be opposite over adjacent. And so this is SOHCAHTOA. Now, of course, it only works if you remember how to spell it. So if you want to mispronounce it in your head in some way to make sure you remember how to spell it, feel free, like so, ka, toa, whatever you got to do to make sure you spell it right. All right, so we know our definitions then of sine, cosine, and tangent. Now we're going to remember how do we use those to figure out things in a triangle. So we're going to be using the same picture to answer these 4 questions. Now, since it's going to be the same picture, go ahead and draw it on your paper. And I'm going to give you a little hint here. Something that I find works really well with these. If I know I'm going to have a picture like this that I'm going to reuse for multiple problems, I'll actually draw it in pen. I know, crazy. In math, we can actually use pen for something, right? But if you draw the picture in pen, you won't erase half your picture when you change your labels. So, on your paper, draw the picture, and at least write down number 1, as that's going to be the first problem that we go through together. All right, so we're now going to go ahead and tackle number 1. So the very first thing I want to do whenever I'm doing one of these problems is I want to label the picture. Now, if you drew your picture in pen, make sure to now break out the pencil, because we want to be able to erase the labels that we're about to put on there for the next problem. All right, so the first thing I want to do is label where C is 70 degrees. Now notice C is a capital C here. As you may recall, capital letters are always used for the vertices, or angles. Lowercase letters are always used for the sides, or side lengths. Now, since this is a capital C, that means we're talking about angle C here being 70 degrees. Now, that's really important to know, because that tells me that when I go and name the sides, it's all relative to the 70-degree angle. It's all relative to angle C there. All right, next up, B equals 10. Notice it's lowercase b, so I go ahead and label side B as 10. And finally, we want to find C, lowercase c here. So that's side C. Now, for my purposes here, I'm going to put a little box around it. Some people will change the label to X, because you always think that you're solving for X. Different people use different things. If you made a new, fresh drawing, you could just label it C, but leave out all the other labels. There's different ways to make it clear. You just need it to be clear so that you remember which ones you're solving for. Now, when I see this picture, this is enough to now do the problem. I just need to know, what do I call these now? So, from the angle that I'm starting from, what do I call my 2 sides? I'll start with the one that I know. What about the 10? What do we call that side of our triangle?
Hypotenuse.
Yep, that's the hypotenuse. Remember, it is opposite the right angle. And so, that's going to be our hypotenuse. And what do we call side C?
Opposite.
Remember, it's relative to that particular angle. So yes, that is on the opposite side. So yes, that is the opposite there. So then, in order to know whether to use sine, cosine, or tangent, we just have to know which of them involves hypotenuse and opposite. That is sine. Because sine equals opposite over hypotenuse. So we're going to do sine. Now, sine always has to be of something. Every now and then, I'll see somebody try to write something like this. They'll say sine equals. That doesn't make sense. That would be kind of like saying square root equals. A square root of what, right? It makes no sense without something inside of it. Sine is the same way. We have to have something inside of sine for it to make sense. Now, what always goes inside of sine is the angle. Every single time. We have to feed sine an angle. So it's going to be the 70 degrees. So sine of 70 degrees equals. Now, in terms of knowing what to put on top and what to put on bottom of our fraction over here, it goes back to the definition. We don't care which one we know or which one we don't know. We don't care which one's bigger or which one's smaller. All we care about is which one is the opposite and which one is the hypotenuse. So, the hypotenuse, actually, opposite's on top, so let's do that. So the opposite is C. So I'm going to put the C on the top. The hypotenuse is 10. so the 10 goes on the bottom. If you wrote it as something over 10 and then wrote the c on top, that's fine. It's just critical that your final fraction here has to be c over 10. All right, so that's looking good. From here, we now need to see how do we solve this for c. There's two different methods that different people use, and they both are fine. One way to do this is you start by multiplying both sides by the denominator of your fraction. So you can multiply both sides of your fraction by, or both sides of your equation by 10. That's fine. But there's another way. And the other way is going to make you realize why I started you off with a bunch of practice with proportions today. Because if you write this as a proportion, so this could be, that means a fraction equal to a fraction, I'd have to write that over 1, but then it would equal c over 10. Well, you've just been practicing solving a proportion a bunch. Remember, we cross multiply. And so if I cross multiply, 1 times c is c. And sine of 70 times 10, that is not sine of 700. The 70 is trapped inside of the sine. The 10 isn't. I can't manipulate them with each other. Another way to look at it, 70 is an angle. 10 isn't. They're not related, so I can't combine those two. So best we can do, write it as 10 times sine of 70 degrees. Once you've done that, we're now at the point where we're going to have to do the calculation. And so you got to break out your calculator at this point. Now, when using your calculator for calculating sine, cosine, and tangent, we must always check that our calculator is in the right mode. Specifically, in this case, degree mode. I remember back in geometry, you had to do this all the time, right? You always had to make sure your calculator was still in degree mode, and you were probably asking, what's up with radians? Why do we care? You'll find out soon. We're going to get into radians later this unit. But for now, yes, have it in degrees. If you're on a TI 83 or TI 84, press mode. You should see degrees highlighted there. If you're on a scientific calculator, you should see DEG displayed at the top of it. So now, when doing this calculation, if you are on a TI 83 or TI 84 type graphing calculator, you're basically going to type it in exactly as you see it. You do 10 times sine 70 equals. If you're on a scientific calculator, it feels a little bit more like when you were doing your logarithms. You got to do the 70 and then press sine and then times 10. You have to do it in the order of operations there. Whichever way you do it, we end up getting 9 point, then we get this really big long decimal. 3, 9, 6, 9, 2, and it's just this big decimal that goes on forever and ever. I don't want to have to write out that whole decimal. Just like when we did logarithms, even if we write down a rounded number in the middle, I got to use the whole calculation at the end, but only round my answer. So I'm going to round that as my final answer. Now it doesn't say what to round to here, so I'm arbitrarily going to choose to round to 2 decimal places. That would cause me to round that to be 9.40. Make sure that you can get that correct answer out of your calculator before we go on. Now as we head into number 2 here, it can be very tempting to say, oh yeah, I got the last one, so this one will be the same. I don't really need to focus on it. No, each of these brings in a different nuance. You're going to see something different happen in this one. Although the basic ideas are the same, the algebra might feel a little different to you. So we want to make sure that we get everything solved. Now the first thing I always want to do is I want to label my picture. So if you're reusing the same picture as before, erase the labels you used for number 1, or draw a new triangle, do one or the other so that we can have a nice clean labeled diagram, because you don't want the labels overlapping each other. And we're going to label this one. In this case, we're told that A equals 30 degrees. Notice it's capital A, so that's angle A. So angle A here is 30 degrees. Important to know because that means that's the angle that we're going to be going from. We know that lowercase a is 14, so that side A is going to be 14 units long. And we're asked to find C. Notice it's a lowercase c, so that's the length of side C here. So again, I'm just going to mark that that's what I'm looking for. Now that diagram is enough to tell me whether I should use sine, cosine, or tangent. And to be explicit and tell how and why it tells us, let's again remind ourselves. I start from this angle. And I need to figure out, what do I call each of these sides? So, side A. What do I call side A?
Opposite.
That is the opposite. Yep. And side C. What do we call side C? It is the adjacent, yes. Notice the hypotenuse in this case is not involved, so we don't care. So I then go back to my trig definitions of sine, cosine, and tangent and ask myself which one of them involves the opposite and the adjacent. And the answer, yes, is tangent. So that's the first thing I write down in my work, is I write tan. It's going to be tangent of always the angle, right? So it's going to be tangent of 30 degrees. Equals, all right, now our definition of tangent is that it's opposite over adjacent. So I put whatever the opposite is on the top. So that means the 14 goes on the top. The adjacent is whatever goes on the bottom. In this case, I don't know what it is. It's just C. And there's my original setup. Now you'll notice what's different between this problem and the last one. In the last one, C was on top. In this one, C is on bottom. Now, you still can start this algebraically the same way that you could have before if you just wanted to multiply both sides by C. You can do that. You can go ahead and multiply both sides by your denominator. Nothing wrong with that. In fact, that's the way I often do it. However, many people end up feeling like they're using two different methods, even though it's the same. So you can always set it up as a proportion, and it'll feel a little bit more similar that way. But again, either method works. I don't care which method you use as long as you do it consistently correct. And so I'm now going to cross multiply. Now when I cross multiply here, I'm doing the tangent of 30 times C. There's nothing really I can combine there. I'm just going to write it as C times the tangent of 30 degrees. And that's going to equal 1 times 14, which of course is just 14. Now again, you'll notice the difference between this problem and the last one. When I cross multiplied in the last one, it gave me C equals. In this problem, I have C times tangent equals. I still need to be able to make it into C equals. So we need to get rid of the tangent. Since I'm currently multiplying C by tangent, I'm going to divide both sides by that tangent. Now I'm saying divide by tangent because I'm being lazy. I'm actually dividing by tangent of 30 degrees because it always has to be by the tangent of something. We can't just divide by tangent as a function. It has to be tangent of 30 degrees. All right, so when I do that, I now have C equals 14 divided by tangent of 30 degrees. Now I know what C equals. Now I know how to put in my calculator. So do that calculation, please. When you do that calculation, if everything went correctly on it, you should get an answer of about 24.25 when rounded correctly. Again, I arbitrarily chose to round to 2 decimal places. You didn't have to. You could have gone out to 3 decimal places and called it 24.249. That'd be fine. It didn't specify. But of course, whenever you're doing assignment or something, check to see what it specifies to round to. All right, and so again, we write down our problem. We start with a clean diagram, and then we start labeling it. All right, in this case, lowercase b equals 12. So I put in the 12. Lowercase a, side length a, equals 8. So I put that in. We're asked to find c. Notice lowercase c once again. And so I'm looking for this. What am I going to use to solve this one, though? Well, there's no angle that we're going from. And you actually only have to use sine, cosine, and tangent when an angle is involved. If there's no angle involved, we can't use sine, cosine, and tangent. So instead, yes, some of you have already been thinking about it, the Pythagorean theorem comes back again. Yes, you can still use Pythagorean theorem. If it's just the side lengths of a right triangle involved, you can still use Pythagorean theorem. You don't have to make it more complicated than that. I mean, you can, but why? So, we need to start plugging in now. Now the key with Pythagorean theorem is remembering that when we write c squared like that, that means equals the hypotenuse squared. Notice this number c here that we're solving for in this problem, that's not the hypotenuse. So it's not whatever side I happen to label as c, it's the hypotenuse. So let's start plugging in. 8 is a, so we got 8 squared plus the other leg squared. I don't know what that is. That's my c. So notice this is now being called c equals the hypotenuse squared. So equals 12 squared. It can be a little weird because we got c here and we have c here, but they mean different things. Remember, in the original formula, c is hypotenuse. In this equation, c is the side that I happen to give the name c. No necessary connection between the two. All right, and so now we solve this through. Of course, we can do the squaring, right? So 8 squared is 64, and 12 squared is 144. And then we're going to go ahead and subtract 64 from both sides. So we got c squared equals 80. And if I want to solve c squared equals 80, well, we solved those earlier this year. That means I got to take the square root of both sides, right? Now, throughout the year, though, I've been drilling into your head, whenever we take the square root of both sides of an equation, we must include the plus or minus. And yet we don't have to here. Just when I get to where you actually remember it, right? Why don't we need it here? Well, what does c represent? This c represents a side length. And at least in this problem, that has to be positive. Lengths are always positive. Later this week, we'll start seeing how we can make them negative, but it's actually because we're turning them into coordinates, not lengths. But since c represents a side length, it must be positive. So I don't need the plus or minus for that reason. Technically, yes, we would have the plus or minus written out front here, but then we'd drop it away later. So I'm just kind of saving that step. All right, so for my final answer here, we have two options about how we can give this as an answer. One is an exact form, which means take the square root of 80 and simplify the square root. Well, you remember how to do that, right? Find the biggest perfect square that goes into 80, 16, and take the square root of that. So it becomes 4 root 5. That would be the exact answer. Or, again, we can go ahead and give it as a decimal here. I'll go ahead and round it again to 2 decimal places. If we did it that way, that would give us about 8.94. This problem didn't specify which way we had to do it, so either one would be fine. When you're doing the problems like on assignments and things like that, always check to see how it specifies for the answer to be presented, because the assignment problems will tell you, give it exact or round or whatever it is. So for our last problem here, we again start the exact same way. We start by writing down the problem and with a clean diagram that we're going to label. So, side B is 9. Side C is 4. But notice that we're asked to find A, but it's a capital A. So that means that we're actually being asked to find out what the measure of angle A is going to be. Let's write that a little more cleanly. So this is what our original setup would look like. Now, notice we will need to use sine, cosine, or tangent here because an angle is involved. Even though we don't know what it is yet, anytime the angle is involved, you will need sine, cosine, or tangent. All right, so again, we start by deciding what do we call each of the sides then. So let's start with B. What do we call side B here? Opposite, adjacent, or hypotenuse? Yep, it is hypotenuse. Okay. Side C. What do we call side C? And remember, we're going from this angle up here. That is the adjacent, yes. So we have hypotenuse and adjacent. All right, so which of our trig ratios involves hypotenuse and adjacent? Cosine. So that's the very first thing I write on my paper is cos. Now remember what we always have to put into sine, cosine, and tangent. It always has to be the angle that we plug into it. Now I don't know what that is here. Well, so I'm just going to call it A. So cosine of A equals, and again, the definition of cosine is adjacent over hypotenuse. So whatever the adjacent is, that goes on top. So that's going to be 4. Whatever the hypotenuse is, that goes on bottom. That's the 9. There's my original setup. Now that I have it here, it won't make sense for us to write as a proportion in this case, because my unknown is not in the fraction. My unknown is inside of cosine, so I need some way to undo cosine. In fact, I need some way to be able to find the inverse of cosine, because of course you remember inverses undo each other, right? We did inverses in the last unit. So how would I write inverse of cosine? Well, remember how I wrote the inverse of f of x? We wrote that as like f to the power of -1 of x. Same thing with cosine. If I want to write inverse cosine, it's cosine to the power of -1 of whatever it is. And so that's how we write inverse cosine. And again, that's how I read it, as inverse cosine. And it means the inverse operation. It doesn't technically mean to the power of -1, it means the inverse. And so what I'm actually doing to this equation here is I am taking the inverse cosine of both sides of that equation. By doing so, we cancel out the cosine on the left, and we end up with inverse cosine of whatever was on the right. And so you'll notice inverse cosine tells us what an angle equals. It gives us an angle measure. So then I now can go ahead and do that calculation. So to do this calculation, again, it depends on what type of calculator you're using. If you're looking for inverse cosine on your calculator, though, it is almost always second cosine. So on a graphing calculator, second cosine 4 divided by 9 equals. Scientific calculator, do the 4 divided by 9 first, and then do second cosine. When you do that, the number you get should be about 63.61. But remember what this represents. This represents an angle. The angle I know is measured in degrees, so include the degree symbol. It's a tiny little detail, but it's an important one, especially since, yes, we are going to start looking at radians here pretty soon. And that little degree symbol, that's how we tell the difference between the two. One last thing to mention. In this case, I undid cosine by doing inverse cosine of both sides. If it were the other way around, if I started with inverse cosine, and now we're having to solve that, you do cosine of both sides. They undo each other. And so feel free to go both directions with that. If you start with cosine, you can use inverse cosine to get at what's inside. If you start with inverse cosine, do cosine to get at whatever's inside.